Hello viewers, I am Naved Ahsan. I am professor in the Department of Civil Engineering at Jamia Millia Islamia, New Delhi. I will discuss today a lecture on image rectifications. As viewers, you may be aware that image data that we obtain through various kinds of sensors, in the case of remote sensing, it may contain different deficiencies or errors. These errors may be due to the internal errors of the sensors or may be due to the interaction with the atmosphere or certain other reasons. So, viewers, this image rectification includes two major components. One is geometric correction and the other is radiometric correction. Geometric correction may have different other components also. So, if we look at geometric corrections, these include errors due to internal as well as external sources. These are also known as systematic errors. The internal errors are systematic errors and their corrections are referred to as systematic corrections, whereas external errors or external corrections are non-systematic. Now, systematic errors may be corrected or rectified by using the satellite ephemeris data as well as certain mathematical models. These discrepancies include: one is scan skew, then it may also include error due to rotation of the earth or earth's rotation, error due to variation in the platform velocity, similarly error due to variation in the velocity of the scan mirror velocity variation. Apart from these, there may be other reasons also, for example, the panoramic, then due to projection systems as well as aspect ratio. So, all of these are internal errors in the satellite data, which are basically due to the rotation of the earth beneath the satellite. It may be because of the movement of the platform itself or due to the deficiencies in the scanners. Whereas non-systematic errors, they may be due to the change in the attitude of the platform, attitude changes which may include the roll as well as pitch or the yaw of the platform, and other may be the change in altitude of the platform or altitude change. As we have discussed that these kinds of internal errors can be rectified by mathematical models, whereas these non-systematic errors, they are very difficult to be modeled, but their correction may be carried out by using certain polynomial equations as well as data from the ground control points. So, we can use polynomials for correction of these data as well as we can also make use of GCPs, that is ground control points. So, we can discuss these. For example, the scan skew, this kind of deficiency occurs in the satellite data when the ground swath is not aligned with the ground track, and this may result in skew in the satellite data. Then Earth's rotation, as we know that during the period of scanning, a certain amount of movement of the earth may take place because of its continuous rotation from west to east, and this may result in the skew in that satellite data. Then variation in the platform velocity may change due to certain reasons, and it may also result in along track kind of error, a scanning error in the satellite data, and so is the case with the scan mirror velocity changes, because it may also vary. The time taken by the scan mirrors in each sweep may vary. So, there may also be along track kind of error in the remote sensing data. Panoramic kind of error may result in, because we know that the ground coverage is not directly proportional to the scan angle that we use for the satellite data collection, but it is proportional to the tangent of that scan angle. Now, because of the variation in the theta, which we may be considered as the tangential scan angle, and theta, although it is approximately equal to the tangent of the theta, but it is not exactly equal to tan theta. So, it may also result in the error in some kind of error in the satellite data. So, the error due to projection may be because of the curved surface of the earth. As we have to transform this curved surface on a plane projection with all the lines perspective being normal to the surface, this alteration from the curved surface to the plane surface may also result in some distortion in the remote sensing data. Then similarly, the aspect ratio, some of the satellite sensors may produce non-squared pixels, which may result in the error of this aspect ratio in the satellite data. And as we have discussed earlier, these kinds of errors may be removed by using the ephemeris data of the satellite, as well as using certain models which can be developed by actually modeling the source of the error. Now, we shall discuss about the non-systematic errors and non-systematic geometric corrections. One of the kind of non-systematic correction is the attitude of the platform. Now, this attitude of the platform is actually, there may be movement in the platform during the scanning. There may be three kinds of movements, as we know. One is the rolling, which may be about this axis, then the pitch, which may be about this axis, as well as the yaw, which may be about movement around this axis of the satellite. Now, these may also result in certain kind of distortions in the satellite data. Similarly, the change in the terrain, the relief displacement or the change in the elevation of the terrain, as well as change in the altitude of the aircraft may also result in this non-systematic kind of error. Now, when we have to remove these errors, we can make use of polynomial equations or transformation equations. The process is therefore called transformation of the image. Which make use of polynomial equations. Now, these polynomial equations may be linear equations as well as non-linear equations. Linear equation may be of simple form. For example, it may be x equal to a0 plus a1 x, or we may write this as capital X. Similarly, y equal to b0 plus b1 y, where a0, a1, b0 and b1 are constants which may be derived from the satellite data itself. Similarly, the second order polynomial or the quadratic polynomial may be also be written in the form that x equal to a0 plus a1x plus a2y plus a3xy plus a4 x square plus a5 y square. And similar kind of equation will be for y coordinates, where a0's will be a's will be replaced by b's, b0 plus b1x plus b2y plus b3xy, b4 x square and b5 y square. Now, the first order polynomial, although it may remove different kind of linear deficiencies from the satellite data, which may be caused by the scan of the data or due to the rotation of the satellite data, this second order polynomial equation may also remove linearities from the data. In general, a third order cubic polynomial is used for remote sensing data for removal of different kinds of error in this data. So, the quadratic polynomial or the second order polynomial can be written as x equal to a0 plus a1x plus a2y plus a3xy plus a4x square plus a5y square. Similarly, the equation may be written for y coordinates, that is y equal to b0 plus b1x plus b2y plus b3xy plus b4x square plus b5y square. Now, this second order equation may remove certain non-linearities from the data. In general, we use the cubic polynomial for removing different kinds of distortions found in remote sensing data, and this cubic polynomial or third order equation may be written as x equal to a0 plus a1x plus a2y plus a3xy plus a4x square plus a5y square plus a6x square y plus a7xy square plus a8x cube plus a9y cube. And similarly, we can write the equation for y also with a's being replaced by b's. Now, this may also be written in a general form. A 3D generalized form of polynomial may be written as x equal to summation I is equal to 0 to m, summation j equal to 0 to n, summation k equal to 0 to p, a I j k, x I y j z k. And similarly, for y equal to summations I equal to 0 to m, 0 to n, 0 to p, b I j k, x I, y j and z k, where a and b are model parameters, capital X, capital Y and capital Z are the cartographic or terrain coordinates. These m and p are the integer values, and they are chosen in such a way that the total sum is generally between 0 and 3, and they govern the order of the polynomial. So, viewers, while using these polynomials, we must understand one of the crucial aspect, that is the ground control points and their selection. In this case, we have to be very careful about selection of ground control points with respect to their numbers as well as their locations in the remote sensing data. Depending upon the type of polynomial that we use, the order of the polynomial, we must have a minimum number of ground control points, which are given by an equation n minimum equal to t plus 1 into t plus 2 divided by 2, where n minimum is the minimum number of ground control points that we require and t is the order of polynomial. For example, if you are using the first order polynomial, in that case t will be equal to 1. So, for first order polynomial, if t is equal to 1, then n minimum comes out to be 1 plus 1 2, then 2 plus 1 plus 2 3. So, this should be equal to 3. Similarly, for the second order polynomial, this number comes out to be 6, and for cubic polynomial you will find that minimum number of GCPs required is 10. Now, apart from these minimum numbers, we must be careful about the selection of the location of these GCPs. In general, minimum 10 to 20 number of GCPs are found to be sufficient, which are spread all over the scene, all over the remote sensing data, including the corners of the image. So, viewers, after the process of image transformation is completed, we need to carry out resampling of the remote sensing data. Resampling is the process in which the brightness values of pixels are assigned on a pixel by pixel basis. The most common method used for this purpose is the nearest neighborhood method, in which we assign the value of a new pixel with respect to the nearest pixel available in the reference image. Simplest method of resampling, the zero order method, is the simplest method of resampling where no computation is required, whereas the other methods, higher order methods, may require averaging of pixel values. So, viewers, next part of this lecture is radiometric correction. Radiometric correction, as we discussed in the earlier part of the lecture, may include different types of errors which are caused by either improper calibration of the scanners or due to malfunctioning of the any sensor. Now, in this case we may have different types of distortions. The first may be called the stripping, and the correction may be referred to as de-stripping. Similarly, the second radiometric correction is removal of missing scan lines. And third may be removal of random noise from the pixels. Apart from that, there may also be correction required due to the sun angle as well as earth sun distance. Then we may also need to correct the data for atmospheric factors, which may be called as atmospheric corrections. So, de-stripping is basically the occurrence, removal of occurrence of strips present in the satellite data. The raw data which we obtain from the satellite may contain a pattern of strips or bands over there. Although all the sensors of the satellite are properly calibrated before the launch of the satellite, but after some period of time there may be deviation of the calibration, and this may result in either low frequency or high frequency in the satellite data, which causes strips in the image. Now, the removal of these strips is called de-stripping. The process of de-stripping requires construction of different histograms for different sets of data. So, if we have to remove de-stripping, we need to construct histogram, for example, for the first, 7th, 13th lines present in the image data. Similarly, we have to construct another histogram for the 2nd, 8th, 14th line in the data, and so on. We may need to go for example, if it is there are 6 bands. So, similarly we can construct histograms for different lines, last being the 6th, 12th, 18th and so on scan lines. Now, after constructing these histograms, we have to correct the values of all the pixels with respect to a certain standard band value, and we can use the equation as dn new equal to sigma d over sigma I dn old plus md minus sigma d over sigma I mi, where dn new is the new brightness value of the pixel, dn old is the old brightness value of the pixel, sigma d and sigma I are the standard deviations for the reference. Sigma d is for reference and sigma I is for the sensor under consideration. Similarly, md and mi are the mean values for standard as well as sensors under the consideration. So, using this equation, we can remove stripes or bands from the remote sensing data. Now, next kind of radiometric correction is removal of missing scan lines. Viewers, you may often find a kind of a streak in the remote sensing data, which generally occurs due to a particular detector in the sensor when it stops functioning. So, it generates a kind of missing line in the remote sensing data. We can easily remove these missing lines by using a simple algorithm, as we can find out the pixel values in the missing lines with respect to the pixel values of the adjacent lines. For example, the dn nu can be found out by dni j minus 1 plus dni j plus 1 by 2. Now, this is a very simple algorithm where we have averaged the pixel values of the two pixels in the adjacent lines of the missing line. dnij minus 1 may be the previous line, the pixel value corresponding to the pixel for which we are computing the new value of the brightness, and dnij plus 1 may be the pixel value for the pixel which occurs in the succeeding lines, and we have simply averaged these two pixel values. Now, there may be another case when there may be two consecutive lines missing in the data. In that case, we can simply replace the data of the preceding and succeeding lines to obtain the pixel values in these two missing lines. If there are three succeeding missing lines in the data, then we can replace the first line with the preceding line in the data, we can replace the third line with the succeeding available line in the data, and then by averaging these two lines we can find out the second missing line also. So, in this fashion we can eliminate the missing lines from the data. Then next is the correction for the noise or removal from the noise in the image. Now, we must first understand what is noise in the image. For that, we take a small segment of the image which contains 9 pixels, and suppose these pixels have dn values as dn1, dn2, dn3, dn4, dn5, dn6, dn7, dn8 and dn9. Now, in this fashion, in this data, if we have to find out whether this particular pixel contains noise or not, then we have to use the equation. We have to find out two different averages which we call as dn average 1 and dn average 2. dn average 1 is the average of pixels on the corners dn1, dn3, dn7 and dn9. So, it can be simply written as dn1 plus dn3 plus dn7 plus dn9 divided by 4, whereas dn average 2 is the average of pixel values which are immediately adjoining to this particular pixel under consideration. So, this should be written as dn2 plus dn4 plus dn6 plus dn8 divided by 4. Now, if the pixel contains noise, then the difference of these two, which can be referred as the threshold value. Now, if the pixel or dn5 is more than the threshold value, then the pixel is considered to contain noise. In that case, the dn5 will be replaced by dn average 2. So, if this dn5 is more than the threshold value, it will contain noise, and to remove this noise we will have to replace dn5 by the average dn average 2, which is nothing but the average of these 4 adjoining pixels. So, in this fashion we can remove noise from the data. The next correction is correction for the sun angle as well as earth sun distance. Normally this correction is applied together. Now before the application of correction, we must understand that the brightness of the pixel will vary with the variation in the sun angle as well as with the variation in the earth sun distance. The correction may be applied by using an equation which gives a combined correction, which is E equal to E0 cos theta 0 over d square, where E is the combined radiance or lumination, E0 is the luminance at mean earth sun distance, and theta 0 is the sun angle, where and d is considered as earth sun distance, which is represented in terms of astronomical units, one astronomical unit being equal to about 150 million kilometers. So in this fashion we can correct the earth sun distance distortions as well as distortions caused by the sun angle. Now next is atmospheric correction. Viewers, you may be aware, when the radiance from the sun reaches the ground, it passes through the atmosphere, and during its travel through the atmosphere, some of the radiance is either absorbed or scattered by the atmosphere. Similarly, the reflected radiance also is absorbed or scattered by the atmosphere. So this affects in two opposite natures. It has effect by absorption as well as it has augmenting effect upon the brightness value by the scattering of data. This may be corrected by using the equation as L equal to rho E T over pi plus LP, where L is the total illumination or spectral radiance recorded by the sensor, rho is the reflectance of the target, and E is the irradiance on the target. LP is known as path radiance, which will also have an augmenting effect upon the brightness value of the pixel. So these are different types of radiometric corrections which may apply on the remote sensing data. Viewers, in this lecture we have discussed about different kinds of image rectification processes, including both geometric corrections as well as radiometric corrections. The geometric corrections, as we have discussed, was due to different errors in the platform or sensors or due to the rotation of the earth, whereas radiometric corrections involves correction for different errors incorporated into remote sensing data by errors in the detectors or improper calibration of the detector or due to atmospheric factors. I hope this lecture would be useful to you. With this hope, I thank you all. Thank you.